Oh, all right. What's up, everyone? I don't really know who's actually still coming, so I'm gonna go over someone's solution to the 2017 question 5. So 2017 question 5, and I want to go through a solution to the 2020 AIMO question 7. And yeah, we'll see how that goes. So hopefully, even though I don't exactly know who's coming, I do think that the people who are coming consistently would have already all done the AIMO, so there should be no problem here. And then we can have like our embargo, be part of this bubble that's extended between us. Okay. Yeah, and it's the week 9, huh? So not many people last till week 9, and which is not much of an excuse this term because it's been all pretty easy. The other term was actually pretty hard because every week depended on the previous week. So to get to term 9 was actually pretty much impossible for most people. But here we do like a new question every time. So yeah, and I'm really happy to have come across a lot of new students this term, especially the ones willing to participate even with assignments due. I'm really happy about that, because it's one less thing I have to teach you, right? So one really important concept that I think especially young people won't understand, especially with their influence by their parents to some extreme degree, is that they have no sense of priority. Okay. Yeah. Okay, so let's have a look at this question. So the question is, okay, so you have some people, maybe you can just not number them 1, 2, 3, all the way up to n times n plus 1. Okay. And then you remove n times n minus 1 people, or numbers, and then you have 2n people left. Okay, and then you reorder them so that from smallest to largest, so you can rewrite them as another 2n numbers again. Okay. Okay, but the original people might not be ordered in ascending height, so it could be like and the goal is to have the 1 and 2 next to each other somewhere. Okay, the 3 and 4 next to each other somewhere, all the way up to the 2n plus the 2n minus 1 person next to each other somewhere, but they don't have to be in that order. So for example, if n equals 2, okay, so if n equals 2, you have 6 people, right? So it doesn't have to be in order. Okay, but the goal is that you have to try to remove, so this is 2 times 1, so 2 people. You have to remove 2 people. So for example, I could remove this guy here and this person here, and see, and what's left. So if you look at their new height order, this is the shortest, the second shortest, the third shortest, the fourth shortest, right? And they're next to each other. Okay. So, okay, and it turns out they're in the right order in their pairs, in their thing, where it doesn't have to be like that. They could have been, like, the 4, 5 could be here and the 1, 2 could be here. And you'll end up with them in the wrong order, right? But the point is, the 1 and 2 don't have anyone in between them, and the 3 and 4 don't have anyone in between them. Okay, so obviously you can, if you haven't tried this question, you can try it yourself a little bit if you want first. But the point of this exercise is to review a student's answer to this question, and maybe this is a good exercise for you to see if you understand what is being said and if you can verify what is being said is correct or not. Okay, so let's have a look. Okay, so it starts with we prove statement by induction. I'm assuming it's on n. Okay. Okay, base case. N equals 2. Yeah, so this is something you should definitely be able to get yourself. So if you haven't tried it, you should try it. But let's have a look. So it says petition the 6 players into 3 and 3, yeah? Consider the tallest 3 players. So the biggest 3 numbers in this case, yeah? At least 2 of them will be in the top. At least 2 of the top 3 players will be on the only one side of the line, yeah? So by pigeonhole principle, the 2 of top 3 on one side. So in this case, can you see like it's 4 and 5, yeah? Yeah, so if you have like a 4, 5 here, there's 2 cases. The first case is if this other person is not a 6, and the one case is if this person is a 6. Okay. So if the thing is not a 6, then what you do is you delete it, and you find the 6 over here, and you delete it. So then you're left with the 2 tallest people and the 2 shortest people. Okay. If it is a 6, yeah. So if it's a 6, then it's actually easier. Like, there's no pressure to do anything. You can remove the same. You can remove the 6 here even, and you have a free choice over here. Okay, because no matter what, the 4 and 5 will be the tallest, and the other 2 will be the shortest. That's the base case. Okay, so this is the base case. All right. So assume is true for n is greater than or equal to 2. Yeah. So I guess it's assume is true for k minus 1. So now we're doing the induction step. Okay. So I mean, this question appears on the 2017 IMO question 5. I emailed this question already. So if you really don't understand the question, you can read it again. Okay, so we want to reduce. So the induction step is we want this k minus 1 times k to imply this k times k plus 1. Okay. Hmm. So what we do is we have k. So this is the case we're considering, right? And we want to reduce it to that case. So we have k plus 1 people grouped you know with in k groups. Okay, so instead of having these people, we have to like this notation might not be necessary. Okay, so let's label the heights of the people. So I guess this is what replaced the numbers. So the original question had heights of people of all different heights, but I think it's equivalent just having numbers. But, okay, so let's do it. Label the heights of the people. A1, So this must be the. Okay, so let the heights of the players be laid in ascending order. And then we have the heights of the first group, the A1. This might be a typo here. Yeah, so there's two ambiguities. It could be the ascending order part, or it could be the groups. So this grouping might not be the meaning the same as that group. Okay. So let the groups, the nth group be all the way up to A, K plus 1, K. So there should be K groups, yeah? I think there's two different meanings of groups here. Okay. So I think what's happening is we're labeling all the people in ascending order, and it's not how they appear in this partitioning, okay? So it's just the shortest person to the tallest person. And then we're grouping the tallest people together. Or is it the shortest? It must be the shortest. Yeah, so we're just ordering them shortest to tallest. Or like remember it was 1 up to 6. Okay, and then this grouping is not the grouping by the partitions, but it's just the grouping of people in the same height category, yeah? And this is like the shortest K plus 1 people. And this is the tallest K plus 1. Okay. Hello. Welcome. Okay, so shortest. Yeah, I certainly wasn't talking about you missing it. I think you almost have a license to miss it because you do catch it up. So mm. Consider the leftmost partition of n+1 players. Okay, so now we're considering this k+1 people here. Okay, so notice there's only there's k categories. There's k height category. So this is k height groups, and there's here it's k partition groups. Partition. So k divided. K groups by like partitions. So there's two meanings. What for today? No, so I think a lot of people had like English assignments stuff due. I don't know. So people even I don't know. They have exams this week as well, depending on what school they go to. But anyway, so we consider that by the pigeonhole principle, there's going to be two people from the same height category. Yeah. So pigeonhole principle, two of same height group. There's only k height groups and k+1 spaces. Yeah. Okay, so when we remove the remaining so all we want to do at the moment is keep yeah, so what we want to do now is to delete all the other people. So the strategy now is to keep these two. So keep these two, delete everyone else, or remove others. And so maybe these two from the same, they came from the jth height group. We delete all the other people in the jth height group, yeah? Mm-hmm. Okay, so we're a quarter of the way into the solution now, okay? A little bit more than a quarter. Okay. Yeah, I guess here we're not sure what the importance of these height groups are because we didn't emphasize it in the statement. But I think this statement needs to be modified. Okay, so it's a modified statement, and I think the statement should be modified as follows. So it's instead of saying we can remove a bunch of people so that the people left can be coupled, the statement needs to read something like we can remove a bunch of people and we can do it in such a way that the people who end up coupled are not only satisfying the condition, but they also satisfy an extra condition, okay? And the extra condition is that the coupled people are in the same height groups that they started in before the people were removed, okay? So in this case, what we want to prove is that the people, so that if the two one of the people in the group of two people is in group J, then the other person will also be in group J after you do the final final coupling. Okay, so that's why we have these groups here, and that's why we're going to be so careful when we're deleting these other things here, because so what happens is you have to be careful to delete the right number of things on the left of group J. Okay, because if there's not the right number of things on the left of group J, then the induction hypothesis won't apply. Okay, so there needs to be, so for example, if J was the very first height group, yeah, then there doesn't need to be anything because once you delete the first height group, the rest is just exactly the lower case. Okay. But for example, if J was the second height group, you might be worried. You might be worried if you've deleted the first height group or not. Okay. So you don't have to worry if there's one person from the first height group because then, or because that one person gone will leave the right amount of people left. Yeah. So if one person from the first height group is deleted from the first partition, then there'll be k people from the first height group left, and that's how many you need for the induction, right? You need k minus 1 lots of k. That's the right amount. So actually, you're worried about. So you're not worried about 2 or more because that'll be you just delete them instead, and make it the first height group instead of the second. But you are worried if there's no one from the first height group because then you're left with k plus 1 from the first height group, and that screws up the induction hypothesis. Okay, I think that's what the comment is here. No, okay, so basically to make sure you don't screw up the partitioning and the induction hypothesis, it's noted that you have to remove. So if it was group 2 instead of group J, you have to remove one thing in group 1. Okay, if it was group 3, you need to remove 2 things that are lower than group 3. So basically, you need to remove J minus 1 people from groups that are lower than J. Okay. Okay, and if you remove J minus 1 from lower, then you're forced to remove like some amount from above, and it'll be the right number. Okay, and I think that number turns out to be k minus 3. K minus J, sorry. So, and then k minus j from taller. Then of course you've removed a certain number of people from j. So if you add that up, it's k minus 1 people have been removed in this way. And there's a whole bunch of people from j that's been deleted. Okay. How many people from j have been deleted? Yeah, but yeah, so you just have to, so this k plus 1, so there could be possibly, k minus 1 people from j that's been deleted. Yeah, so maybe this statement could also include the people from j, because if the people from j are in here, you have to account for them differently. Yeah. So I guess the point is you have to remove j minus 1 shorter, k minus j taller, and you have to remove the other ones in j. And these all have to happen. So they may happen through force, where they happen through having to remove the other ones here, and having to remove the j's here, or they happen by choice, okay, where you've removed a lot of j's here that you didn't expect to have, but now you have the free choice to try to satisfy these conditions, okay? So the statement is still correct. It's not that there have to be this many taller and that many shorter outside here. They could be in here, or they have to be a lot of the time in here, because you don't actually have control of what's in there, right? Okay. Yeah, so I might have to adjourn this for a slight second here. Okay, so if it's possible to do that, then the induction hypothesis can be applied. Okay, so we're up to the point where now we have to say, so it might not be just whatever j that comes up by the pigeonhole principle. It just guarantees that it's possible to get some j at all. But we need a j to satisfy those other removal conditions. Okay, so now the rest of the proof is going to be to show that it's possible to pick a j that repeats here that satisfies the conditions that allow the induction hypothesis to act. Okay. Okay. Okay, so let's adjourn for a little while. For 10 minutes, you might want to catch up your thoughts on this problem. Mm. Okay. So let me just write up something and we'll have to adjourn for a second, okay? So in this first partition of K minus define a sequence B1, B2 up to BK, where BI is the number of people from the first group, where B1 equals number of people from first group. B2 number of people from second group, etc. Oh yeah, so yeah, so I guess you have an example here. If you have, say, like if there was 8 people in the first partition, yeah, and they were corresponding to first group, fourth group, seventh group, first group, second group, fourth group, first group, sixth group. Maybe you can try to figure out what the B's are. Okay, and then how to sort of characterize the condition and how to solve the problem. Yeah. So I'm gonna take a break here. I'll be right back. Yeah, so I'll be right back. If you're really waiting for me, you can try to basically um if you can try to finish off this notation and the proof, and you can also try to chord bash the other question. You know. All right, I'm back. It's like this time next week. Yeah. Yeah, so that'd be exciting. Though it might not be like real time. Okay, so let's continue where we left off. Yeah, sorry about that. There's some stupid school rules make me have to pick up the kids. All right. Yeah, so in this notation, what are the B's? So we're saying that the first group, these are the first group, these are the fourth group. Okay, so there's three. So there's three people from the first group. Okay, so B1 equals 3. B1 equals 3. B2 equals 1. B3 equals 0. B4 equals 2. B5 equals 0, and B6 equals 1, and B7 equals 1. So the sequence of BIs is 3, 1, 0, 3, 0, 1, 1. Okay. Okay, so what's next? 3, 1, 0, 2, 0, 1, 1, 0, 0. Yeah. That's exactly what the thing says. Okay, good. So an explanatory example. So if there's a 2, we are done if the sum of the numbers on the left of the 2 equals the number of terms to the left of 2, because the construction is satisfied. Yeah, so a 2 just means, wait, that's a 2, not a 3. Okay, so a 2 just means there's a repeated 2, and so you can use that if there's the right number of things on the left of it. So if there's j minus 1. So this is the fourth group. J minus 1 is 3, so there should be 3 things, okay? Okay, so that doesn't work, okay? But here the first group has at least a 2, and there's nothing to the left of it. And so it's open, so that's already satisfied. Okay. Yeah, so if we put this on a graph, so I guess the graph would be B. The graph would be like Bn versus n. Yeah. So you have a y and an x. Y equals x is like that. Yeah, so actually y is not Bn, it's the sum of the Bn's up until n. So it's the sum of the Bi's up until n. So it's a cumulative graph. Okay. So in this case, I guess it'd be 3, 0. So it would go 1, 2, 3, 4. I won't list them all out, but it would be on the first one. It would go all the way up to 3 already, and then it would go 4, and then it would go 4 again. And then it would go 6 like here somewhere. Okay. Yes, I think the most important statement here is um, the condition is equivalent to being one above the line y equals x. You know? So 1 above the line y equals x means so for example we have 2 here would make it at least 1 above the line y equals x. You know? If you had a 1 and then a 2, it'd be a 1 above. Yeah. So the condition is need 2 to occur at least 1 above. Okay. And so if there's a 3, I think it's the same condition. Oh, okay. So I guess there's an issue of being exactly 1 above. Yeah, so it should be exactly 1 above for the right number of things to be the left of it, because you need to minus 2, right? You want there to be j minus 1 on the left of it. So if there's 2 and there's exactly 1 above, then it's the right amount. Okay. Yeah. Well, what happens is if there's 3, you don't have to. If there's 3, you don't have to be exactly 1 above. You can be 2 above because you can use that third one to do whatever you want it to do. Okay. So there's 4 you can be above. So what I mean by like you need the more than 2. The first thing that's more than 2. You need something that's more than 2 to occur at a place that's at least 1 above y equals x. Okay. And if you're not considering it as like the first one to overcome the line, then you might also need it to be within the right amount of that point because you have to get back down to that point. Okay. Okay, so now I guess the student is addressing it case by case. Um, so if you have a 2, it should occur just 1 above. If it's 3, it should occur 2 above. Well, at least it could be 2 above, but it can't be 3 above because you can't get back down. Sorry, You can't get back down to the one above by just using one of them, you know? So that's the problem. Hmm. Yeah, I guess when there's a triple, you can't quite be in the right place. You have to be either, um, well, yeah. So if you're on the right place, you have to delete one to make it. Hmm. Yeah, I guess so. Yeah, it could be two apart. Yeah. Yeah. So I guess in the graph it says if there's just a single two, then it basically has to end up like on one of these spots from somewhere. Yeah. Whereas if it's a three, it could end up at like the spot above here, or it could even end up above that. And if there's a four, yeah. So this the if it's a three, it should have the same slope. Okay. So if there's a four, you can draw three lines of the same slope to represent that it could be one above, two above, or three above. Okay. And so you can see what happens with five, six, or whatever, however big the number gets. It's parallel lines that can get it further and further above. Okay. Okay. So now the point is, once you add it all up, there's going to be n plus one. There's going to be k plus one. Okay. When this becomes k. Okay. So the final point on the graph is going to be above y equals x. It's going to be k plus one. Okay. And the starting point, I guess, it's 0, 0. So there's going to be some point which it crosses y equals x. Okay. Yeah. So I think we can clean up the cases in this argument by just saying by finiteness, there'll be a first time. Yeah, so by finite, there's the first point for which it exceeds the y equals x line. And to do that, that has to be a 2 or more, yeah? Yeah, and because for it to exceed the line, it has to have a slope of 2 or more, because otherwise it would just keep going along the line or across, right? So you know that the point which it exceeds the line has to have a 2 or more, okay? And I think that's basically enough. Yeah. And so at that point, if it's more than one above, you can just use the free choices to bring it back to the right level. Okay. Yeah, so this is a really good write-up. Well, the graph was really Edwin's idea, and so this is actually Edwin's write-up. So that's a really good way to represent. Otherwise, it could be a very complicated argument, right? So it has a point that's above, it doesn't start above, and there's going to be a first point which exceeds. Okay. Okay. So the next part, I'm assuming you've done the AIMO. So if you haven't done this, close your eyes and ears. Mm-hmm. What's going on? Was it 36 and 9? Okay, so I want to talk about this AIMO question, and I don't know, I thought it was just natural. It was kind of nice because it was kind of exactly the stuff we learned like the day before the AIMO. So um, I thought it was kind of appropriate. Yeah, so we have this question where you have like a flat piece of ground and a wheel. Is it a wheel? I don't know. And the radius is 36. And you have a smaller wheel that's just touching, right? And then you have finally another wheel that's here. So basically, this is 2020 AIMO 7, yeah? Um, yeah, so I thought this question was kind of neat because it was naturally exactly all the things that we learned 2 days before the test, okay? So basically the question asks, what is the area of this triangle? So you have a triangle like that, yeah? Um, so what was it, like DEF or something? DEF. Um, the question was, so this was 36 and this was 9, okay? The question is, what is the area of DEF? Okay. Yeah, so I think we learned this exactly like 2 days before this exam, right? And I think also if you don't like chord bashing, I think whatever your solution might actually be equivalent to a chord bash, because if you're doing Pythagoras, you're really just doing the distance formula, right? So I thought so. This is kind of a natural chord bash because there's so many right angles. Okay. Yeah. So if we make the origin here, which is pretty normal, okay, then D has, well, D has some. Does D have obvious coordinates? Yes. So D would be 0, 36, right? Yeah, I'll show you. So I mean, basically, this thing here, right? Um, well, and it's also question 7, so you don't even have to prove anything. You just have to get the answer. Okay, so you don't even have to state stuff like this goes. The center joins the point of contact and all this stuff. You don't have to even worry about that. You just know it's true, and you don't even have to state it. Okay. Yeah. So the nice thing about chord bashing is the right angles. Okay, and you know everything's at right angles to each other, and you also basically have all these right angles here, right angles, and basically, I mean, intuitively, you know that because the two circles are fixed, right? The radiuses are fixed. The fact that they're arranged this way, it fixes the center E, right? So you can figure out what the center E is just from knowing the radius of the two circles. So that should be obvious. Um, so you can let the center E be like, it's already got y value 9, so you can have like E 9, yeah. Okay, and how can you find them? Well, you basically have a distance formula, right? So it's 36. So it's E squared plus 27 squared is equal to 45 squared, right? So E squared is equal to like 45 minus 27 is 18 times 72, yeah? So that's equal to 36 times 36. So E is equal to 36, okay? So we have E equals 36, 9, yeah? Ah, did we mention the Heron formula in this class or another class? Or you're talking about another class? So we've definitely mentioned all the formulas needed to solve this problem. Okay, so now it goes. So now, like you're gonna figure out the coordinates of f, right? So the coordinates of f, you have basically. So f is in the same situation that E is in with D, right? Except you don't know the radius. But if you knew the radius, you'd know where the center would be, right? But then f is also touching the circle E. So you have basically the same two conditions to work with, so you can find an extra piece of information, including the radius. Yeah. So what I'm saying is, if you let the coordinates of f, so f, I guess it's f9, right? Oh, you don't know the radius, so I'm not gonna say fu, f radius. No, I have done that in an exam once. Um, yeah, so check it out. to find out f and r, you can just do the distance formulas, right? So, for example, like f squared plus 36 minus r squared is equal to 36 plus r squared. Okay, and here it's 36 minus f squared plus 9 minus r squared equals r plus 9 squared, yeah? So you can solve these two simultaneously to find f and r. Okay, so for example, here you have f squared equals 2r times 72. We had a good observation. And here you have 36 minus f equals 2r times 18. Yeah. Yeah, so you can go from here in a lot of different ways. So one way is, for example, okay, so you know 36 is bigger than f, right? Because f is this, and 36 is the whole thing. So you know how to take the square roots here. So you have 36 minus f equals, and then that's 6 root r, yeah? So actually this approach, this particular calculation here was Orlando's idea, which was pretty good, okay? And similarly, you could do f equals, so this is now 12 root r, okay? So if f is 12 root r, we can sub in for f, and we have 18 root r is equal to 36, so root r is equal to 2. Or you can sub in that for half f, and so 3 on 2 f is equal to 18. And 72 on 3, what? So f is 72 on 3, which is 24. Yeah. Yeah, so you get that f equal to 24, 4. Yeah? Yeah, and so basically what Habing is saying about the trapezium and stuff is the punchline of this. It's basically how coordinate geometry, remember we learned this in Barry Bash. So now the area of triangle DEF is equal to half times the determinant 1, 1, 1, okay? And then you put the x values, DFE. So 0, 24, 36. And then you do the y values, 36, 4, 9, yeah? Yeah, actual application in the exam, yeah? So shoelace formula. So it's half is 1 times 24 times 9 minus 4 times 36. So I don't times numbers out unless I have to, yeah? And I do minus 0 times 9, which is 0. And then plus, so it's plus 36 times 36. And then plus 1, and it's 0 times 4, which is 0, minus 36 times 24. Okay? Yeah, it is the same thing, right? So from one formula to another, how would you do this? Well, I certainly wouldn't times anything out. Okay, let's divide by 2. We have 12 times 9 minus 2 times 36 plus 18 times 36 minus 18 times 24, yeah? So I could have been a bit more generous. So here I could do 12 outside of 9 minus 6, yeah? Plus 18 outside of 36 minus 24. Uh, can you even see this still? The board is still. So where the board is. Oh, the board is. The camera angle works better for some reason right now. So that's 3 times 12. I'm still not going to times it, okay? Plus 18 times 12. Oh, hopefully I haven't made a mistake. And so this is equal to 12 times 21. Um, is that what people got? So this is 210 plus 42. 152. Did I miss? Is this right? Yeah, see, real life application of abstract nonsense. No, it's not. Yeah, abstract nonsense is taken. I'm sorry. I think we're going to go through question 10 now because Sean was going to complex batch it. So, but we can do like synth. Okay, so are we? Okay, so that's pretty nice. Yeah, it all worked out. Okay, so maybe. What's Q10? You have a circle, a semicircle. All right, so this is the center, I guess. Something like this. Is that the question? Wait, you mean like do this? Oh yeah, there's lots of 90 degrees, huh? C. Is that what you mean? C? Oh. Um. C X B. Oh, A B X C. So like this is like A prime, B prime, C prime, X prime. Yeah, I'm actually quite excited to explore this complex bash of question 10, especially since it's something we've been talking about quite a lot. And when I looked at this, I did see like potential. There's only one circle, so there are angles. There's lots of 90-degree angles, but so what are we doing? Complex bash. Okay, so x equals c plus c bar. Wait, why is x c plus c bar? Oh, it's 2 times. Are we using the red or the black? All right, let's use the red, okay? Let's just see. No, we just don't label this stuff. Oh, we can label these A bar, X bar. Okay. So complex numbers, you can see that like, so C bar would be like the reflection, right? C bar. Okay, so we're letting the origin be O, yeah? Let O be origin, and the circle is the unit circle, yeah? OA equals 1. So, and then obviously OA is also the x-axis. Um, and then this is the x-axis, yeah? real axis. The x is equal to, so c plus c bar on 2 would end up here. Because that's that's the real value of c, and then twice the real value is x. So x equals c plus c bar, yeah? And then complex dash. Okay, so a equals 1. That's nice. Oh, this is looking fantastic already. You've solved like all the variables already. There's only, you still got to find either c, or you got to find c, I guess. That's solve for b. Oh, okay. Solve for b. B. So could you use some angle condition to get b? What did you do? OCX and XBA are similar. OCX and XBA. OCX is similar to XBA. Yeah, that's cool. I think that's a, yeah. So O minus C. What is this? O minus C on X minus C. So O minus C is this vector on X minus C. Okay, yeah. It's that vector must equal X minus B on A minus B, yeah? Okay, good. So then this is, A is just 1. I don't know if you want to sub in, so you can sub in that, I guess. So C bar. That's just minus C on C bar equals X minus B on 1 minus B. Alright, so this gets you B in terms of C. So C bar is minus C squared. Alright, what are we doing algebra to get? So right hand side. Oh, so you're actually just literally solving for B. Okay, so yeah. So minus C squared. Yes, minus C squared plus BC squared equals C plus C bar minus B. Yeah? So then um, b outside of c squared plus 1 equals c plus c bar plus c squared, and then b equals c plus c bar plus c squared on c squared plus 1. Yeah? That's equal to c 1 plus c squared plus c cubed on c I guess c cubed plus c. Oh, so you just do the b's on the unit circle? Uh-huh. Let's have a look. So b has length 1. So b times b bar equals 1. That's 1 plus c squared plus c cubed, c cubed plus c, and this is times 1 plus c bar squared plus c bar cubed on c bar cubed plus c bar. Oh yeah, so you can solve for c, yeah? So I guess 1 equals, that's 1 plus c squared plus c cubed. We can take out one of these c's, I guess, c squared plus 1. Take it over here. It's c bar squared plus 1. And then you have 1 plus c bar squared plus c bar cubed. And then that's equal to, so it's still 1 on c squared. Maybe I can put the 1 on c squared on the other side now. 1 on c. That's too confusing, I'm sorry. I don't want to confuse people, but whatever, I don't care. 1 plus c squared all squared equals 1 plus c squared plus c cubed times c squared plus 1 plus c bar. Yeah. So c times 1 plus c squared all squared equals 1 plus c squared plus c cubed times 1 plus c cubed. So for C, is this what you ended up with? Hmm. Yeah, would it be nice to keep the C bars? Maybe I want to explore it from this point. Did you expand it with the bars? Hmm. Okay, we'll explore this alternative. Okay, so you're saying just expand it. Okay, so C plus 2C squared cubed plus C to the 5 equals 1 plus C cubed plus C squared plus C cubed plus C to the 5 plus C cubed plus C to the 4 plus C to the 6. Okay, so C cubed, 2C cubed, C, C, C to the 5. We got 0 equals 1 plus C squared plus C cubed plus C to the 4 plus C to the 6. Is that it? There's no C to the 5. You can either keep 1, 2, C cubed. No C to the 5. What do you do? Like minus C cubed equals minus C cubed times 1 minus C squared equals what is it? C 1 minus C to the 8. is a second degenerate solution of 60 degrees. What? XPA becomes a dot. XPA becomes a dot. Wait, if XPA becomes a dot, oh, you're saying it's an isosceles triangle, it's an equilateral triangle, the dot. Oh, okay. So if it could be an equilateral triangle, 60 degrees, then C would equal to um. You're saying C could equal to root. So e to the I pi on 3. So half plus root 3 on 2i. Does that work? So if that happens, then c squared, so c cubed is 1, right? C squared is minus, c cubed minus 1. So then c cubed plus 1 equals 0. And then so then c squared, so c squared plus c to the 4 is also equal to, so c cubed equals minus 1, yeah? So you have c squared minus c plus 1. Yeah, that equals 0 too. Yeah. Oh, so this should be a factor. That's what you're saying, right? So it has to be a 1. We have, oh, that's 4 there. It's got 2 terms, or has it got 4 terms? Or minus c. And c to the 5. So it's going to create a minus c to the 5. You have to do a plus c to the 5. So there's a plus c cubed. And you're going to minus c to the 4. c squared. Yeah. Let's see, and c to the 5. So that's the cube plus c. Needs to be a c to the 4. Mm-hmm. So I guess I'm going to erase this. Yeah, so basically if it's a non-real root, it should come in conjugate pairs. So this is a factor, yeah? Okay. So let's just try to factorize it, okay? So 0 equals 1 plus c squared plus c cubed plus c to the 4 plus c to the 6 is equal to 1 minus c plus c squared. Okay, so what are the roots? So the sum of the roots are 0 there. So the sum of the roots here is 1. The sum of the roots is 1. That's, yeah. So the sum of the roots is 1. So the sum of the roots here is minus 1, right? We know that. Yeah, we know that already. Something 1. Okay, let's have a look. So you get like a c to the 4, c to the 6, you get that. You get no c to the 5s, which is what you want. You get a 1. Okay, now about the c to the 4. So you get 1 c to the 4, but you get a minus c to the 4. So you need another c to the 4, yeah? That's one way to get it. So you have that. You have 1 c to the 4 minus c to the 4 plus c to the 4. So you get plus c to the 4. Okay, now you want c cubed. So you got c cubed minus c cubed. You need a plus c cubed, yeah? What's this saying? So this is saying if you times the right-hand side by 1 minus 1 plus c, 1 minus c, so 1 minus c squared, you should get something. So this is saying c to the 5 equals 1. Yeah? Yeah, so I guess out of all the angles, pi on 5, so 2 pi on 5 is the next one. 3 pi on 5, 4 pi on 5, and then just pi. This is 2 pi on 5, 2 pi on 5, 4 pi on 5, 8 pi on 5. So pi on 5 is 36 degrees. So this is 72. This is 144. This is 3 times that, 216. This is 4 times that, 284, 288. So then C is the only angle in the first quadrant, yeah? So I guess if they didn't specify degenerate or non-degenerate, then it's missing a solution, or it's missing the solution where C is where it's 60 degrees. So it could be 60 degrees or 72 degrees. Oh, there's a diagram in the question. Okay. Hmm. Yeah, I mean, this is not an easy factorization to see. Oh, okay, yeah. So you're saying if you measured it with a protractor or a makeshift protractor, um, well, would you have to draw the diagram to scale, or is it already drawn to scale? Okay, but if you measured it, then you would know it's c to the 5 equals 1. You know that's a factor, and then you can check that. Yeah. Um, yeah. If you knew the answer was 72, you could prove it very easily. Yeah. So this gets you. So the c could be like on this side as well. I get that. That's the other one. I don't get the 4 pi. I guess that's the reflection here, but so it's the four different. It's the four different quadrants that give you the four different solutions to that, right? And the four degenerate case. Well, there's only two degenerate cases. How come there's not more degenerate cases? I mean, so I can see that the four solutions for C here are they meant to be like 1, 2, 3, 4, right? And then these two solutions for C are here. Oh, okay. It's here and then here, right? Yeah, it has to be. It's only two. Wait. Yeah. So when it's equal to -1. Yeah, like the other one's here. Yeah. So the one here doesn't work. It can't. It can't be like 4. It's just that one will give 1 instead of -1. So it's here and here. That'll give -1. Okay. Yeah. Yeah, that was pretty cool. I mean, yeah, it's a shame going from here to here in the exam would be very tough. It's like 15 terms, and only 5 of them survive. Yeah, so this is technically it's not cyclotonic, but it's not off by much. Hmm. Actually, I do want to see alternative. Let's see what happens. So what happens if we explode it like this? When we got to here, what happens if we got c squared plus 1, c bar squared plus 1? Mm, Okay, so if you don't do the bars thing first, you get 1 plus c bar squared plus c squared plus 1 1 12 plus 1 plus 1 9 terms, yeah, plus c bar. Yeah, I think you might have to clear that anyway. Let's have a look. What if you got C bar? C plus C bar plus C cubed plus C bar cubed, or not 7 with 2 more. C squared, C bar squared, yeah? Zero equals 1 plus C bar plus C cubed plus C bar cubed. It doesn't really make a difference. It does. Yeah, I don't know this helps. So C plus C bar. Hmm. 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 Yeah, I think if you get rid of the bars here, it's the same. Hmm. Oh, so you're saying this is the two real codes alpha. 0 equals 1 plus 2 cos alpha plus 2 cos. What is this? You expanded it. Yeah, I guess this would be like one of those complex number exercises then, if you put it in terms of cos alpha. What would it be with the cubes? Hmm. And is this the same condition as saying, if we use another condition, would it give you the same? It should, right? Because it's always the same. So what if you use the condition that would kind of not degenerate when b is what if you use like the right angle condition? Like what if you try to say like b plus 1 is perpendicular, so b plus 1 on a, yeah, minus b. What if you said a plus 1 on b minus 1 was 90 degrees? So some multiple of I. So you have 1 plus b on 1 minus b, the conjugate. What was b again? Is this the same? What was b again? Something on c plus c cubed, yeah. What was the expression for b? Oh, it was this thing. One plus c squared plus c cubed. So if you did that plus 1, so b plus 1 or minus b. C 1 plus b is 1 plus c squared plus 2c cubed. And then 1 plus b on 1 minus b. And so it's 1 plus c squared plus 2c cubed on c minus 1 minus c squared. So that could be interesting. This thing came out of this. If you take the bar, plus c bar squared plus 2c bar cubed I don't know if it is. Is this true? If it was 0, would it also be true? Yeah, I guess. If that was 0, yeah. So this looks like that. There's a common factor here. Mm-hmm. So this is equal to that. So let's put this all over c outside of c minus c squared minus 1. So that's c cubed. And that's plus. This is c plus c squared plus c cubed plus 2c4, yeah? You see, it works out differently. And I think the reason is because it doesn't allow the degenerate case. So this gives you 2 outside of 1. See that? So that degenerate case is really tricky. And I think, so the condition here is AB is perpendicular. If you say that, it seems to automatically take care, it seems to divide out the degenerate case. Yeah, so I just did the same thing you did, except instead of using the condition that, um, instead of using the condition that, instead of just saying B was on the unit circle, yeah? I guess I said that it makes an angle of 9 degrees, which is kind of like saying it's on the circle, but it means, but to get the 9 degrees, you can't divide by, the B can't be equal to A. Um, yeah. It's actually strange that it's different, isn't it? So, yeah, I mean, so in principle, this equals 0 would still satisfy the equation. But I think to get that expression, you have to divide by b minus a, or a minus b. Yeah, I mean, it'd be impossible to distinguish between them in like the exam. But if you had done it with that, it would have gotten you straight to there. Hmm. Yeah, harder way with the harder method. Yeah. Yeah, I mean, how else could you do it? You could get lucky in the other method if you subbed in like c cubed equals -1 and really hoped. I guess see like another thing is also yeah. So another thing also, I guess. So the condition that it says, so saying the condition like saying the condition that b is on the unit circle is not quite the same as saying that it makes an angle of 9 degrees also, right? Because saying that is on the unit circle contains the information that it makes an angle of 9 degrees. But saying that it makes an angle of 9 degrees extracts out that information at the same time. So it might give you the information in another form, yeah. And I think the entire question is a form because it was the form of the answer that made it impossible to factorize, right? So if you could try to change the form of the condition, you might have a chance. So it's actually very subtle, right? Like the difference between being on the circle and being 90 degrees. So to realize that angles in a semicircle are 90 degrees with complex bash, what would the actual thing be? It'd be like one. How would you complex bash that theorem? It'd be like one plus b on one minus b. How would you even show that? What is the bar of this? This is 1 plus b bar on 1 minus b bar. And this is equal to 1 plus, so it's b plus 1 on b minus 1. Yeah, so it's exactly the negative. So that should be true anyway. Oh, yeah. Yeah, I definitely think you would have gotten it if you had more time, yeah? The time is annoying. Hmm. Hmm. Yeah, maybe just naively, it's like if you do the mod b squared, that's like an order 6 equation, whereas, yeah, I don't know. It's a 1 minus b. Actually, we don't have that much time. I need to point out a mistake I made, actually. I need to point out a mistake I made. Um, okay, so I don't know. I don't really do this that much, hopefully, unless it's just not noticed that much. But for 2015 IMO2, I made a mistake when I said, so I had it was BC minus A equals 2 to the N. AC minus B equals 2 to the M. And AB minus C equals 1. And then this is odd. And this is even. So I made a mistake in claiming that. So when you take out the 2's, it was the A prime. So you have A prime and B prime are the odd parts. of A and B. I said something in the argument. I said like one of them is 1 and the other one is 3, and therefore these expressions are the same. Okay, mod 4. Which is obviously not true, right? Because this is like 1 times 3, and this is 3 times 1. Sorry. 3. Hold on. What? Wait, what am I doing? So I have A prime equals 1 mod 4. B prime equals 3 mod 4. Wait, did I actually make a mistake? Hold on, let me just. B squared is 1. Yeah, so this is equal to 1, right? And this is equal to 3. So they're not equal. Okay, I said they were equal. Yeah, and no one pointed it out at the time because I guess everyone was busy doing like exams or something. And so I guess currently we have basically nothing for that question then. So yeah. So the actual question itself, if people want to try it, is 2 to the L, and basically find all triples. Okay, and it doesn't have any conditions on them. But yeah, so I'm sorry to say I actually made a mistake yesterday. I claimed that this was equal, and I guess everyone was either absent or too tired to point it out. And yeah, and I even made a comment like this was different than what I wrote down in the notes. And I guess it's different because it's it's not true. Okay, so this is a question that's kind of interesting, just because it looks kind of similar to a lot of those easy AMO questions we've been doing, but seems to be quite difficult. Yeah, so I don't know if I have that much more to say about that. Yeah, so basically, let's say over here. So actually, I don't know if people are interested in actually thinking about this. This could be interesting to think about. So you have A, B. So let me just try to. So you have A, B, C integers, and then you can maybe do A, B is less than C. Then you have L is less than M is less than N. And we have BC minus A equals 2 to the N. AC minus B equals 2 to the M. And AB minus C equals 2 to the L. Okay. Question is find all A, B, C. So far we've found 2, 2, 2, and 2, 2, 3. This is greater than or equal to 0. Yeah, and I'm kind of happy. Like I was gonna end it early, but also the possibility of not ending it early and just staring at this for half an hour is fine with me. I would love to hear any ideas. I'll have my dinner. Oh yeah, I don't know if I mentioned, but it was Edwin who pointed out my mistake. Yeah, because he actually went back into the stream and watched it. So it's a good thing some people actually watch it. Does this do anything? Hmm. Hmm. Yeah, so I guess this looks nicer. I just don't know what we've done here. So, see, I guess I like this step for one reason is that before, like if you have like A and B and C even, you want to cancel out a 2. You can't because there's degree 2 over here and only degree 1 over here, right? But if you write like this is degree 2 and degree 1, but at least they kind of appear with the same degree on the side of the equation. So definitely this implies this. Okay. Or like the original equation implies this. But it's not so clear that implies that. Okay. But yeah, so what I like about this kind of equation is you can take out a factor of 2 until basically L's are gone, right? So if A, B, C even, yeah, then it comes out, you can have so B on 2 squared minus A on 2 squared equals 2n minus 1 A on 2 minus 2m minus 1 B on 2. Seems to help a bit. Oh, so we already proved actually that the number of 2's in C is equal to L. We know that. Okay. And we know the number of 2's in B is equal to M. I think we're assuming they're even, but we didn't even need to for the top one. It turns out they all have to be even. Well, yeah, I mean like L could be 0, I guess. So yeah, so and then we had that V of A was less than or equal to M. We know we had that. So if we try to solve these equations instead, I think you can basically assume L equals 0. And C is odd. If you're only looking at this equation. So if any of them are odd, they're all odd. So if C is not odd, then they're all not odd. Okay. Well, and then I can't exactly remember. Those two can't be 1. Like they can't be zeros. This can be a 0. That'll be a 1. So it's possible this reduces it to the case where C is odd. It's possible this reduces it to that case. At least for these equations, yeah? So you have basically this goes away. This goes away. hmm Yeah, so if C is odd, for example, is equal to 1 mod 4, A and B can only have like 1, 2 between them. That's not going to work. One of them has to be odd, and the other one's even. That's not going to work. So C has to be 3 mod 4, and there has to be a lot of 2's to go around. Mm-hmm. I'll just write the bottom line. I'll keep this B squared minus A, C squared minus B. Hmm. Yeah, I guess we have lost some information. We do have basically just 2 equations. Hmm. Whew. So what happens if C is odd? If it goes odd, we have C squared plus C equals A squared plus 2 NA. C squared plus C equals B squared plus 2 to the MB. Huh. It's a little bit bizarre. that actually a reason? How did we even get that equation? C squared. Yeah, they're all equal to ABC, you know? ABC. So basically, if I write C prime to be the odd part of C, C outside of C plus 1 equals A outside of A plus 2 to the n equals to B. And divide all this stuff by lots of 2's. So if you do this thing here, C plus 1 on 2 to the 2m equals B prime plus this is 1. Yeah. So the C is odd. C is odd, yeah, so it's already C prime. It's already C prime. It's already C prime. So C plus 1, C prime plus 1 has at least 2m equals 2m plus mu B prime plus 1. But we also have mu of C prime plus 1 equals 2n plus mu of A prime plus 1. B prime plus 1, how many 2's can it have? It has a lot. It has enough to make up the difference in n and m. What if the difference is only 1? Hmm. 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 Yeah, I think it looks like time for bed. So congratulations on making it to week 9. It's much too soon, huh? And then the term is over next week. Hmm. So I feel like eliminating C or something is not too bad as well. So C plus 1 is AB. Hmm. I wonder if the other thing could be fixed. Hmm. Anyway, And we'll just take it slow. Um, yeah. If people are interested in kind of getting together for the IMO somehow, maybe that could be arranged. So there might be some worthy people we can add to the Discord. Okay, and it's kind of clearly emerging who those worthy people are as we get towards the end of the term. Yeah. Yeah, I'll have to see how the questions get leaked, but yeah. I feel like the IMO, mm, I remember last time they released the questions like on the same day. I don't know.